Swayam Prabha. Digital India. Educated India.
So, in my previous lectures, I have discussed about the linear approach for 1D ground response analysis, and I have discussed two cases. One is uniform undamped soil on rigid rock, another is uniform damped soil on rigid rock. And we have observed that in case of undamped soil on rigid rock, that you will get the amplification factor can be infinite for kh value pi by 2, 3 pi by 2, 4 pi, 5 pi by 2 and so on. But in case of damped uniform soil on rigid rock, the amplification factor cannot be infinite, because the denominator is always greater than 0 due to the presence of damping. And you have already observed that amplification factor decreases with kh. As kh value increases, the amplification factor or the modulus of the transfer function that decreases with kh. So now in this class, I will discuss about the equivalent linear approach and the nonlinear approach, because in the linear approach you can see that the shear modulus is taken as constant. Okay, it is not changing, because your strain or shear stress is a function of z, I mean depth, and the time. Okay, but as it is a uniform soil is considered, so here shear modulus is taken as constant throughout the depth, and it is not also changing with time. Okay, so it is constant, it is here assumed. But in actually, I have already discussed, that in my previous module, the shear modulus will also change with strain, and strain means as your time will increase, then the time of the loading, seismic load will increase, the shear strain will also increase, and your shear modulus will also change, and damping will also change. So that is been already discussed in the previous module. So in my next approach, that I will discuss about the equivalent linear approach. Okay, so here what we have to do is that here shear modulus, as I mentioned in the previous case, your shear modulus is not function with time or strain. Okay, but actually the shear modulus changes with time, or as the seismic load increases, that means your shear strain will also increase, and the shear modulus value will change, or basically it will reduce. So I have already discussed about the modulus degradation curve. So now in the equivalent linear approach, we will consider the change in shear modulus with time also. Okay, so but it is done in equivalent linear approach. So what we will consider, that I have already discussed that your G by G max, G in equivalent linear model, G by G max changes with shear strain, or that is a shear modulus degradation curve. So say that is this is your G. So this G is the second modulus. So this is my shear modulus. Okay, and this is shear strain. and you know that shear modulus changes with strain, shear strain is like this. So, this is my shear, this is either you can say this is the shear modulus or the G by G max also you can consider. Okay, in that case, either you can plot the G with shear strain, or you can plot G by G max with shear strain. In that case, you should know the G, and I have already discussed how you should know the G, how you can estimate the G. So, if you know the G, then at any strain level you can determine the G max. So, G. So, that means to do this equivalent linear approach, you have to first generate this shear modulus degradation curve. Okay, and it has been already discussed how you can generate this curve for the soil or the location that you are doing this ground response analysis. So, these curves should be available. At the same times, for that soil, the damping ratio and the shear strain curve, that should be also available. Okay. So, this is your damping ratio, and that you know that it increases with strain. Okay. So, this is the two curves. This is G by G max or versus shear strain, or G versus shear strain, or this is your damping ratio versus shear strain. So, now these two curves are available. Now, in previous case this G was not changing, so we did not consider the effect of strain on this shear modulus, okay, because shear modulus is dependent on the strain, or dependent on the other factors also that we have already discussed. So, we consider all these things and generate these two curves. Now, first step for equivalent linear approach, the estimates initial value of G and damping ratio. That means, first we will consider a initial value of G and the damping. So, that we will consider that. So, generally that we can take, say that this is G is equal to G max, because this is the one where this value G by G max value, this is 1. So, that means initially we consider the G max, say. So, initial for first trial we consider G equal to G max. Okay. Generally it is considered that G equal to G max. So, that we say as this is my first trial, we are talking about G1. Similarly, we will consider about the damping 1. Okay. The initial trial we consider the G1, which is generally taken as the G max, and then we consider the first trial damping ratio, generally it is taken as the lowest value of damping. So, that means in that case this will be our G1 for first trial, and this will be our this will be our damping ratio for the first trial. Clear? So, now we consider these two value and we then compute the ground response. Okay. So, that displacement we can get, because I have already given you the expression in the previous lectures. So, I am say you consider the same case, okay, or cases that we have considered, that uniform soil with on the rigid rock. So, the same way you will get the response, the settlement, okay, horizontal displacement. So, that you will get the response, and from there you can get the strain at any point, you can get the shear stress at any point, because you have assumed a shear modulus and the damping ratio. And if it is the damp case, if you consider, then you will get the damping ratio, you will put there, you will get those response. So, that means we will get the compute the ground response including the time history of the shear strain. We can get the variation of shear strain with time, because now we know from the previous case, if you see the expression, the shear strain is a function of z and t. Okay, so for at any depth, you can determine the variation of the shear stress and shear strain with time. Okay, so that means you use the first trial, assume G and the G value and the damping ratio, and then you get the ground response, and then from there you calculate the time history of the shear strain. Shear strain, you know that del u by del z. So at any depth you will get that shear strain, so that means the shear strain versus time history you will get. Now the effective shear strain is determined from the maximum shear strain in the computed shear strain time history. So we will get that shear strain's time history for that particular soil. So from there I can get what is the maximum shear strain. Now that maximum shear strain can be utilized to get the effective shear strain. How I will get that? So I will get the effective shear strain from the that maximum computed shear strain time history, and from the computed shear strain time history you will get the maximum strain. We identified the maximum strain, from that maximum strain we will get the effective strain. So this effective shear strain will be R strain into that maximum strain. That is for first trial. Okay. Now where R strain is the ratio between the effective shear strain and maximum shear strain. Now R strain depends on the earthquake magnitude as proposed by the expression of this R shear strain. So if you want to do it for any particular magnitude, then you can get the R strain, okay, and that R value you can put here, and you know if from the shear strain time history plot you will get the maximum shear strain, so you will get the effective shear strain. Okay. So the next step will be from the effective shear strain, new values of G and damping ratio are selected for next trial. So that means when you calculate the effective shear strain, the new shear strain, if that effective shear strain is the same shear strain corresponding to which you have taken or assume you G and damping, then it is okay. Okay, you can stop the trial there, but definitely in the first trial it will not come. So that means, for example, in the first trial, this is my shear strain that I have considered. This is the shear strain, and after this computation we will get the effective shear strain, say here. This is my effective shear strain. Effective shear strain. So this is the same as here also. This will be my, say, effective shear strain. Say this is effective. So that means I have assumed a shear strain here, but my effective shear strain is coming here. So that means it is not matching. So that's why in the second trial, what I will do, I will now take the G value corresponding to next trial corresponding to this effective shear strain 1. This is I am getting from here. For first trial I am getting effective shear strain 1. So this is my effective shear strain 1. Now I am assuming or taking that shear modulus and the damping ratio for the trial 2. So now my G2 will be this value for the trial 2 and damping ratio 2 will be this value for this trial. Clear? So I will repeat this process again. So from the effective shear strain, new G and the damping ratio are selected for next iteration. Okay, and steps 2 and 4 are repeated until the computed values of G and the shear modulus and the damping ratio in 2 successive iterations fall below some predetermined value, or you can give some tolerance value if your values of these or the difference between the shear strain from 2 successive iterations fall below that tolerance value, then you stop your program. Okay. So, now you can see, for example, now I have taken, this is my second trial, this is my damping ratio, this is my G2 is the your shear modulus. But now after doing that, I will get a effective shear strain, say here. So, this is my effective shear strain for 2. So, corresponding this is say effective shear strain, effective, so this is effective shear strain 2. But I have assumed my, in the second trial, this was the effective shear strain, but after the iteration, I am getting the new effective shear strain here. So, they are not matching, there is a difference. So, now in the third trial, I will take, this is my G and this is the, say, damping ratio and this is my G. Okay, this is G, say 3. Now, I repeat this process. Now, I will get a effective strain, say here. This is say effective strain 3. So, this is corresponding, this one is the say effective strain 3. So, now this you can go for the next trial and then you can consider this is your damping 4 and this is say G4. So, you repeat it again and then now your effective strain, next strain will be very close to effective strain effective 3. So, now effective strain 4 will be very close to, in between, definitely effective strain 3 will be definitely in between 2 and 3 and it will be very close to 3 and so on. Okay. And unless the difference between the effective strain computed from 2 successive iterations fall below a predetermined values or very small value, then you stop it, and that will be your shear modulus and the damping ratio for that particular strain, and this way you can complete the ground response analysis. Okay, so that means here your ground response analysis is not G is not constant, it is function of shear strain also. Clear? This is function of shear strain also. So, this is your equivalent linear approach. Clear? So, there are some few notes are there that 5 to 10% difference are achieved in 3 to 5 iterations, and effective shear strain has been found to be in between around 50 to 70% of maximum shear strain, and effective shear strain is often taken as 65% of the peak shear strain. So, from this analysis you will get that this iteration process you will get the effective shear strain will come in between 50 to 70% of the maximum shear strain, and generally effective shear strain is taken as 65 of peak shear strain, and that I will discuss in detail when I discuss about the liquefaction analysis. Okay. The approach is coded in the computer program called SHAKE. The determination of transfer function has also been coded in SHAKE. Okay. So, that is for the linear approach that, or the nonlinear approach, equivalent linear approach. These program, this total program is coded, or this total iteration process is coded in the program called SHAKE, and determination of transfer function has also been coded in the SHAKE. Okay. So, now I will discuss about the linear approach, but before that there is a term which is called deconvolution. What is the meaning of that? That is the computation of bedrock motion from the known free surface motion. So, now it is in the opposite, reverse. So now, till now what we are doing? We know the bedrock motion. Now from the bedrock motion, we are determining or computing the free surface motion or ground motion, because in the bedrock above that there is a soil, or there may be a different conditions, those I have discussed. So from there, if I want whatever the location I want, from there I will get that that motion. So till now we are doing from the bedrock motion, we are getting free surface motion. But here now, if your free surface motion is known, then from there we can get the bedrock motion. Okay. So this is useful when actual ground motions are recorded on the surface of the soil deposit. So now in the previous case we are considering the ground motions are recorded at the bedrock. Now if it is recorded on the soil surface, then from there I can get the bedrock motion. Now response at any point can be related to the response at any other point. So this way, so suppose for any point, so for example, if you know the free surface motion, from there you can get the bedrock. If you know the bedrock motion and that bedrock is continue to another location, so from that bedrock motion you can get the free surface motion of that another location also. Clear? So that means from the bedrock to the surface, surface to the bedrock, and if the bedrock continues to another location, from there, from that bedrock you will get the another surface motion for another location. Okay. So that means the response at any point can be related to the response to any other point. Okay. So that is called deconvolution, and now I will discuss about the linear approach. Okay. So in the linear approach, definitely the equivalent nonlinear approach, you know, in my previous lectures I have discussed, or the previous module, that you're actually G value changing at every point along that hysteresis loop. Okay. So that is G10 that is every point, but the G sec is the average shear modulus of that particular loop, and this way I can get this G sec at any point, and the G10 also you can get along that loop. So and then from the backbone curve also you will get the G10 and the G sec along that points. So that means your backbone curve we are getting that points that we are getting, and from there we will get basically that your shear modulus and the shear strain, or shear stress, shear strain, and from there you will get the different shear modulus also. So now in the nonlinear approach, what we are doing, so, and remember that in the previous cases I have considered only two cases in previous approaches. I have considered the uniform soil in on the rigid rock, undamped and damped case, but that can be uniform soil on elastic rock, damp, undamped case. It can be layered soil also. So all the cases you will get, you can apply this approach, but I have discussed two of them only. So now in the nonlinear approach, I am also considering one particular, say, soil layer which is above the bedrock, which is this is my bedrock. Okay, so this can be again rigid rock, it can be elastic rock also. Now in the previous cases I have considered only the rigid rock, here also I will consider only the rigid rock. Okay, so this is my soil, okay, whose density is rho s is the density of the soil, and VSS is the velocity of shear wave of the soil. Similarly, the density of rock and velocity of shear wave of the rock, that can also be written. So now here this S means soil, R means rock. Rho is the density and Vs is the velocity of shear wave. Now these soil layer is being divided into n number of small segment or thin layers. Okay. So, this is say n number of thin layers. So, this is n number of thin layers, this is the downward direction is the z, and this is, say, if you note it first, second, then it is I plus 1, this is say n, this is n plus 1 and so on. Okay. Now, horizontal equation for the horizontal motion at the bedrock, we can write that del tau is the shear module, shear stress by del z, that is equal to rho del square u del t square. Okay, that so this is the expression. U is the displacement, and rho is the density, tau is the shear stress, t is the time, z is the depth at any depth. Now, u del square u, that I can write rho del u dot, that means del square u, that I can write del u dot, okay, and del t. This is the expression. Now, if I apply the forward difference scheme, okay, then so this forward difference scheme is a finite difference approach. So, this forward difference, central difference, backward difference, so that can be applied. So, here I am using the forward difference scheme, which is what? Suppose if you have different points, say suppose say this is I plus 1, this is I minus 1. So, at any thing, suppose d y dx, okay, that is this is the del x. So, that I can write y is a function. So, that I can write that y I plus 1 minus y I divided by 2 del x. Okay. So, this is your no, this is del x only. So, this is my forward difference scheme. Okay, that means we are going in the forward direction, and backward difference scheme, so dy dx will be y I minus y I minus 1 divided by del x. Okay. Similarly, the central difference scheme, that is also dy dx, that is equal to y I plus 1 minus y I minus 1 divided by 2 del x. Okay. So, these are different schemes, along with I will use the forward difference scheme, and remember that this way I can determine the d square y dx square, d cube y dx cube, or I can express in your finite difference schemes. Okay. So, now here if I use the forward difference scheme, then your del tau by del z, that can be written as tau I plus 1, that I have written, and it is a function of I is along the z. So, that means tau is, that I have shown in your linear approach also, that the tau is a function of z and t. Strain is also function of z and t. Okay. Now, here your g is also function of z and t. okay, if it is a non-linear behavior of the soil if we consider. Okay. So, one soil sample where G is constant along the depth, then G will be only function of T, and if it is the layer soil, then G will be function of T and Z, because G will also change with Z, and even a single layer, if G value changes, that then also G is a function of your Z and T. So, here tau I T minus tau I, this is I and function of T. So, it is for a particular time we are applying the finite difference scheme along the Z, okay, depth. So, this will be del Z, Z is this small segment, okay. Similarly, del U dot by del T, that will be equal to U dot. Now, this is for a particular Z, it is a function of T plus del T. I mean, we are using the forward difference scheme here also. This is U dot, that is for a particular depth, that is I, and this will be comma del T, sorry, T, because del T is the increment. This will be T, because I here you have written I plus 1. Similarly, here T plus del T. Del T is the increment, which is same as del X here. So, this is your del X or del Z. This is del T. Okay. So, whereas del T is equal to small time increment. Okay. So, that means here U I T, which means that U Z equal to I and I mean I into and Z equal to I into del Z for that particular thing, and this is T. So, that means at any point you can get the Z value if you multiply the del Z with the number of with I. Suppose here the second case your Z will be Z, and third here del Z will be 2 into del Z. Here it will be, next one will be 3 into del Z. So, del Z will keep on adding, okay, if your this increment is same or this thickness of each layer is same. So, now that is the case. So, this is your IT means. So, now if I now put this value, then I will get that your rho U I T plus del T, this is divided by del T minus U I del T, that is equal to tau I plus 1 T minus tau I T and divided by del Z. Okay, now if I simplify that, or if I write, then I can write that U dot, this is U dot, this is also U dot. Okay. So, if I simplify that, then I can write that U dot I U dot I T plus del T, that will be equal to U dot I T plus del t divided by rho del z into tau I plus 1 t minus tau I t. Okay, this is the equation. Now, for if I apply the boundary condition, okay, if I apply the boundary condition at z is equal to 0, that means at the top. So, then at z is equal to 0, that is at I is equal to 1, then mean tau 1 will be 0, because at the boundary condition z equal to 0 means at the top, at the surface where shear stress is 0, shear strain is 0, that I am consider. So, if I put that boundary condition, that at the boundary that shear stress is 0, tau is 0, so it will be u dot I is equal to 1 t plus del t, that will be equal to u 1 t dot plus del t divided by rho del z into tau 1 is 0, tau 1 is 0. So, it will be only tau 2 t, only tau 2 t. So, this is one boundary condition. Now, my next boundary condition at the bottom, okay. So, if the rock is rigid, we have considered, so that rock input motion, because here now from the rock I will go to the top. So, I mean here I am doing from calculation from bottom to the top, because my known ground motion is the rock, bedrock motion is known. From the bedrock motion I want to determine the ground surface motion, okay, or free surface motion. So, that means my input motion is say ub at t, okay, that is input motion. So, in that condition I can write that u dot n plus 1 t, this is my last node n plus 1, which is basically here it is the bedrock, which is the same common node for the soil and the rock. So, here if the rock bedrock motion is known, automatically that will be treated as the u dot n plus 1 t, that will be equal to qb t, okay, that is the known bedrock motion. So, now if the soil deposit is initially at the rest condition, then your soil deposit is at the rest condition, then your u dot I t will be 0, u dot at the rest condition, there is nothing, initially soil is the rest condition, but when your ub t, that means this has some velocity, then automatically this node will have some velocity, then u dot n t, u dot n minus 1 t and so on, they have also some non-zero value. That depends on this boundary condition. Now, from this I can calculate the incremental displacement in each time step, that will be your del u I t, that is equal to u dot I t into del t, because u dot, if I multiply u dot with the t, then I will get the u. This is velocity basically. Velocity if you multiply with the time, then you will get the displacement. So, that is the incremental displacement at each time step. So, at any depth, that is the del u I and del u I t equal to del u I t into del t. Now, how you get the del I t? Because this equation, because I have derived this equation. Now, in this equation, if you apply these two boundary conditions, then you can calculate from this bedrock motion input, you can calculate the u value at any point. Okay. So, that means here, or u dot value at any point, at any I, at any time interval. So, that means at each time interval I know the u dot value from this equation. From this equation I will get that value. So, now this u dot value I will multiply with del t, and then I will get the time increment and displacement, incremental displacement on each time step. Now, if I add those displacement increment, summing the incremental displacement, it will, the total displacement can be obtained. So, if I add this incremental displacement, okay, at each time step, then I will get the total displacement. Okay, then I will get the shear strain. How I will get the shear strain for each layer? Okay, the shear strain will be I t, that is equal to your del u I t by del t, del z. So, this will be, you know, that u I plus 1 t minus u I t divided by del z. Okay, so now, because from this incremental displacement I will get the total displacement, okay, for any time step, and then when I get the total displacement means the u. Now, from the, when I know that u for a different level with each time steps, then I can calculate what would be the shear strain at that level for that time step, or each time step I can calculate the shear strain. Now, when we calculate we know the shear strain, then from there I will get the shear stress also. Now, for the linear case, you know that if it is soil behavior is linear, if the soil behavior, soil is linear, soil response is linear, then shear stress, your IT is only function of GI, not the time. Time is, it is not changing, and then that will be into strain at any point at any time step. So, only G is the function of only the depth. If it is changing with depth only, if it is uniform, then only G, okay, or G max, that I will consider. It is constant, it is not changing with time. So, that is why if it is a linear case. But now, if it is a non-linear case, then G is also function of time, it is function of I and T. So, in that case, that non-linear, the shear strain depends on the current shear strain as well as the stress strain history. Okay, as well as, okay, here stress strain history is not required. We are getting only the current shear stress. But here it is the current shear strain is required and the stress strain history is also required. So, in such case, the cyclic stress strain relationship are used, or we can use that advanced constitutive model to get that the proper shear strain of the soil, or to simulate the nonlinear behavior of the cyclically loaded soil. So, there that shear strain, stress strain history is also required. Here linear case it is not required, but the nonlinear case the cyclic stress strain relationships are also required, or stress strain history is required, and obviously the shear strain is also required, and the not only strain, here strain, if you know the strain and the G, you will get the shear stress. But if it is a non-linear case, then your strain is required as well as the shear stress strain history or the shear stress strain relationship is also required. So this is for the first trial, and then the next, for the what would be the integration scheme. I am just giving you the flow chart, that at the beginning of each time steps, velocity and the total displacement are known for each layer, that I have discussed. Now the velocity and the total displacement are known for each layer. Velocity, where I am getting, that is my rock input motion velocity. From there I can calculate the other velocity for other layers also. Now determine the shear strain for within the each layer, that I have also discussed how we will determine the shear strain. Now stress strain relationship is used to determine the shear stress at each layer. When I get the shear strain, now you use the stress strain relationship for nonlinear case to determine the shear stress in each layer. Input motion is used to determine the motion at the base of the soil layer at any time, at the time t plus del t. Okay, next step, that input motion, that will be that that n plus 1 node, that node, the input motion will be determined at the base of the soil layer, that is n plus 1 node or layer at the time t plus del t. The motion for each layer boundary at the time t plus del t is calculated from bottom to top, that I know that if you know that n plus 1 velocity motion, then you will get the motion of n node, then from the n minus 1 node, and so on. The process is repeated from step 1. The step 1 means the first step. Okay, this first step, this is step 1, to determine the response to the next time step. So this way, at every time steps, I will get the response. Okay, so this is the total your nonlinear scheme approach also. Now you remember that if the soil behavior is linear, then this stress strain relationship is not required. If you know the current shear strain and you know the G value, you just multiply it, you will get the shear stress. But if it is a non-linear, then you should know the shear strain as well as the stress strain relationship should also be known, that you have to use and get the shear stress, because your G value is also changing. Clear? So these are the all three approaches that I have discussed: the linear approach, equivalent linear approach, and the non-linear approach. But remember that I have discussed only the 1D case. There are also 2D cases and 3D cases also that I am not discussing here. So in the next class, or this is the end of this module, in the module 4, in the next class I will start about the module 5, which is the another very important aspect of geotechnical earthquake engineering, that is liquefaction. Thank you.